So what if I told you that, like, the absolute secret to getting a 12-year-old to genuinely understand complex biology or structural engineering isn't a better textbook?
Right, which is what we always default to.
Exactly. But what if it's actually having them draw pictures
Yeah.
and document their surroundings like some, 19th century explorer?
It sounds totally counterintuitive, I know.
Right. Because if I ask you, the listener, to picture a middle school science classroom right now, odds are a very specific and probably pretty dusty image pops into your head.
Oh, for sure.
You're likely picturing rows of desks, a teacher up front pointing at a whiteboard, and a textbook is basically thicker than a brick.
Yeah, the classic setup.
And in that room, you were basically just a human tape recorder. Like you sat there, the teacher spoke, you frantically wrote down a definition for mitochondria, you memorized it for Friday's test, and then...
Yeah, completely dumped it from your brain by Monday.
Exactly, gone.
Yeah, and I mean, that was the standard model for a really long time. It was an entirely passive experience. The learning was something that just happened to you. You were receiving these established facts rather than actually, engaging in the messy, active process of scientific discovery.
But today, we are taking a deep dive into a completely different universe. We're looking at this massive shift in how science is actually being taught.
It's a huge transition.
It really is.
Yeah.
And we have this fascinating stack of sources to guide us today. Curriculum documents, teacher guides, philosophical frameworks, and specifically we're unpacking a project called SIPS.
Right, which stands for Stackable Instructional Embedded Portable Science.
Which is a mouthful. But it's this framework that's currently reshaping classrooms in places like Alaska, Nebraska, and Alabama.
Yeah, it's spreading.
And within that SIPS framework, we are looking at this highly specific, totally immersive 7th grade life science learning system called Bioforge.
Which is such a cool name, honestly. And, the overarching theme connecting all of these source documents is a transition away from that passive classroom you just described. They're moving to what the creators actually call a living field station laboratory.
A living field station laboratory.
Yeah. So in Bioforge, the student is no longer an audience member. They are the lead investigator.
Oh, wow.
And to get them there, the entire system is organized around this very specific sequence of scientific action. It goes, notice, learn, investigate, make sense, and save the evidence.
Notice, learn, investigate, make sense, save the evidence.
Exactly. That is the engine driving this entire curriculum.
Okay, I really want to break that sequence down today because I want you, listening right now, to really think about your own science education and prepare to see how entirely different and honestly, how much more rigorous it looks today.
It really is rigorous.
But before we get to the cool stuff like the actual field station setup, we kind of have to understand the bones of this thing.
The foundation, yeah.
Right, because the documents mention that the required SIPS curriculum provides the instructional spine. And it says it's tightly aligned with the next generation science standards. But what does that actually mean in practice? Like, how do they avoid just handing kids a new, updated list of facts to memorize?
Well, they do it by fundamentally changing the structure of a lesson through a framework they call three-dimensional learning.
Okay.
So instead of just learning isolated facts, students have to operate in 3 dimensions simultaneously.
That's complicated.
Well, those dimensions are disciplinary core ideas, science and engineering practices, and cross-cutting concepts.
Okay, hold on. That sounds like a lot of academic jargon.
It does, yeah.
Break those 3 down for me like I'm a 7th grader.
Fair enough. So think of the disciplinary core ideas as the what.
Okay.
This is the actual subject matter, things like the water cycle or cellular respiration or gravity.
Actual science topics.
Right. Then you have the science and engineering practices. That is the how. It's the physical or mental actions a scientist takes, like analyzing data, developing models, arguing from evidence.
Okay, so the what and the how was the third one?
The third dimension is cross-cutting concepts. These are the underlying themes that connect all the different sciences together.
Like what?
Concepts like cause and effect, or energy and matter, or structure and function.
Ah.
What's super fascinating in the source text, specifically in this one document called the misconception map, is that it points out a major pitfall in the older way we taught science.
Which was?
We used to treat these cross-cutting concepts just as vocabulary words, like you memorize the definition of structure and function and move on.
Right, totally.
But in the SIPS framework, they act as rigorous analytical lenses. You look through them to understand the world.
I'm trying to visualize this. So instead of treating biology and, say, structural engineering as totally separate subjects, The cross-cutting concepts are almost like the grammar that applies to both.
Oh, that's a brilliant analogy. Yes.
Like if a kid understands the grammar of, I don't know, energy flow, they can see the exact same underlying pattern governing both a biological system and a human-built environment.
Yes, exactly. So if a student is studying a food web, they map out how energy transfers from the sun to a plant, to a mouse, to a hawk, right?
Right.
But if they take that exact same analytical lens, that same grammar, and look at a city grid, they can map how electrical energy flows from a power plant through substations to individual homes.
Wow.
They are actively building that connective tissue between disciplines.
That structural spine sounds incredibly rigorous on paper.
It is.
But let's be real for a second here. You can have all the analytical lenses and three-dimensional frameworks in the world, but if a 12-year-old is just, like, staring out the window on a random Tuesday in November, you've completely lost them.
Oh, 100%.
So how does this curriculum actually capture their attention?
And that is exactly where that sequence we mentioned earlier begins, the very first step, the notice phase.
Notice.
Because you can't just walk into a room of 7th graders and announce, today we are going to learn about the conservation of matter.
Right. Cue the eye rolls.
Exactly. You have to anchor the concept in reality. So every single unit in SIPS kicks off with what they call an anchor phenomenon.
An anchor phenomenon.
Yeah, it's a real-world, observable scenario that immediately prompts the students to start asking questions and collecting data.
And the examples in the materials are just wild.
They're so good.
Like, to understand chemical reactions,
Yeah.
they don't just, mix random clear liquids from a textbook experiment. They actually bring in a regular, fluffy loaf of bread and a dense loaf of yeastless Irish baking soda bread.
Yes.
Or, to figure out the flow of energy and matter, they investigate an actual physical owl pellet.
Which kids love, by the way. It's gross but fascinating.
But I have a really practical question here. Because we did lab experiments when I was a kid.
Sure.
But usually the teacher just told us what was going to happen beforehand. We followed a little recipe, and we got the expected result.
The whole point was just getting the right answer.
Right, so how is looking at flat bread or picking apart an owl pellet any different from that? How does it prevent a student from just checking out and waiting for the teacher to give them the answer?
And this is such a crucial distinction. In the older model, the lab was basically just a physical demonstration to prove that the teacher was right.
Yeah.
In Bioforge, the student does not know the answer when they start. Instead, the task is broken down into this chain of student sense-making.
Sense-making.
Yeah, so let's take your baking soda bread example.
Okay.
The teacher doesn't stand up and say, today we're learning about acid-base reactions. They just present the 2 loaves of bread and ask the students, what do you notice?
So they might be like, this one has big holes in it, and this one is literally a brick.
Exactly. And from there, the prompts guide them through the next phases. Learn and investigate.
Okay.
The students might be asked to investigate the actual ingredients of both loaves, and they notice, oh, the flatbread uses baking soda and buttermilk. The next prompt challenges them to model what happens when those 2 specific things interact. So through their own investigation, like maybe physically mixing the 2 and observing the gas release, they build the cognitive bridge themselves.
Oh, I see.
They discover the chemical reaction that created the gas bubbles, which created the holes in the fluffy bread. They aren't confirming a fact the teacher told them. They are actively explaining and designing solutions.
Okay, that is so much cooler. They have to do the actual heavy lifting of figuring out the why.
Exactly.
And I noticed in the curriculum that this sense-making isn't strictly limited to a traditional Western laboratory context either.
No, not at all.
Because the documents explicitly emphasize that local phenomena and indigenous knowledge are deeply integrated into these lessons.
They are, and it's done very intentionally and very respectfully with proper attribution, tying into things like the Alaska cultural standards.
That's awesome.
Yeah, so for example, in an astronomy unit where students are modeling the apparent motion of constellations across the seasons.
Oh, right, I read about that. The curriculum brings in the Micmac and Iroquois stories of the Big Dipper, right, or the Big Bear.
Exactly. And the story of the hunters chasing the bear across the sky actually perfectly aligns with the seasonal position of those stars.
It's essentially an incredibly accurate scientific model.
Exactly. And by using these cultural narratives alongside their own spatial models, the students see that indigenous knowledge is a valid, highly accurate model of observation over time.
It's not just a myth, it's science.
Right. It shows them that science is this fundamental human endeavor. And there are multiple rigorous ways of observing and making sense of the natural world.
That is just fascinating. So, okay, we've got this strong instructional spine, and we've got these incredibly engaging anchor phenomena. But I really want to know what this looks like on a daily basis.
The day-to-day grind. Yeah.
Right. Let's talk about the actual Bioforge classroom experience, because the premise here is so unique. The sources say that when students walk through the door, they aren't even treated as students.
No, they enter as apprentice scientists.
Apprentice scientists.
Yeah,
You
the
think-
physical environment and the whole mindset are entirely reframed. The classroom acts as a laboratory, a field station, a design studio, and a scientific workshop.
Wow.
And Bioforge is what provides the classroom rhythm and that student experience.
Oh.
And to support different types of learners, which, as we know, is absolutely vital in a middle school setting, they use highly predictable routines. They don't just throw open-ended chaos at the kids.
Right, because if you just give a bunch of 12-year-olds owl pellets and say, go investigate, you're going to end up with a huge mess, not science.
Exactly. It would be a disaster.
So what is the actual rhythm of the week? How does this class work from Monday to Friday?
So Monday through Thursday usually follow a very deliberate 4-part cycle.
Okay.
First is the journal launch, where they set the day's objective. Second is targeted instruction, which is this brief, focused moment of learning a new skill or concept.
It's an off 40-minute lecture.
Yeah, no, very quick. Then third is exploration and sense-making, which is the bulk of the class where they are actually investigating the phenomenon. And finally, reflection and evidence capture, where they document what they actually figured out.
Okay, that cadence makes a lot of sense for Monday to Thursday. But Friday is totally different, right?
Completely different.
The documents outline Friday as a day entirely dedicated to, like, synthesizing the week's work.
Yeah, Fridays focus heavily on revision, updating their portfolios, checking in on their badges or standard checkpoints. They might have one-on-one conferences with the teacher, and they do independent exploration.
So it's a breather, but a productive one.
Exactly. It's a day built specifically to process and organize all that evidence they've collected during the week.
And the main tool they use to collect that evidence brings us right back to that journal launch you mentioned. Because it seems like the single most vital tool in this entire Bioforge ecosystem is the field journal.
Oh, absolutely.
And I have to say, looking at the descriptions, this is not your typical spiral notebook where you just, like, doodle the Batman logo in the margins.
Not at all. These are working scientific records. They contain observations, questions, sketches, data, models, explanations, and revisions.
It's serious business.
It is. And the philosophy documents actually root this practice in historical context. They call it the Grinnell tradition.
The Grinnell tradition.
Yeah, connecting it back to people like Herodotus and Pliny the Elder. But specifically, Joseph Grinnell was an early 20th century biologist who formalized this highly rigorous method of field documentation.
What was his method?
Well, he realized that a brilliant observation or a collected specimen is scientifically useless if you don't document exactly where, when, and how you found it.
Wow. It sounds like they are treating these kids like actual pre-professional researchers.
They really are.
It shifts the notebook from being, just busy work for the teacher to an authentic historical scientific task.
It totally does. And to help the students process complex information in these journals, the curriculum relies really heavily on the cognitive science concept of dual coding.
Dual coding. I am not familiar with that term. What is dual coding?
So essentially, the human brain processes verbal information and visual information through 2 separate channels.
Okay.
In the Bioforge journals, students are required to use both. They use text, which the research calls logogens, and they use sketches, which are imagens.
Logogens and images.
Right. And by making the brain encode the exact same piece of scientific information, both verbally and visually, you create redundant memory pathways.
So they just remember it better.
Way better. The information sticks around much longer.
Okay, I can totally see how drawing a cell and writing a description of a cell is better than just doing one or the other.
Exactly.
But I have to be honest. Here is the problem with that. Middle schoolers are incredibly self-conscious.
Oh, yeah.
If you tell a 7th grader to draw a cross-section of a plant stem, half of them are going to immediately freeze up and say, I can't do this, I'm bad at art. How do you get past that anxiety?
And they anticipated that. That's where the ABC rubric comes in. And it's just a brilliant piece of scaffolding.
ABC rubric.
Yeah. Bioforge projects are judged by science, evidence, reasoning, and revision. They are not judged on decoration.
Okay, that's a relief.
So the ABC rubric clearly defines the expectations for a sketch. Accurate, big, and colorful.
Accurate, big, colorful. I love how simple that is.
Exactly. The sketch doesn't need shading, it doesn't need perfect perspective. It just needs to accurately show the parts in relation to one another.
Right.
It needs to be big enough to clearly label the parts, and it needs to use color to distinguish different elements, like, making the arteries red and the veins blue.
That makes so much sense.
Yeah, these sketches are just meant to be imagistic traces that help the brain store structural relationships. It completely lowers the barrier to entry without ever lowering the actual scientific rigor.
And speaking of rigor, I was reading their policy on technology and AI in the classroom, and it is fascinatingly strict, given how modern the rest of this curriculum is.
It's very specific, yeah.
Like, technology and AI can be used to support access, like text-to-speech, or to help with organization and research, or even revision.
Right.
But the policy states unequivocally, technology may not replace observation, evidence gathering, reasoning, source evaluation, or reflection.
Because it defeats the whole purpose.
Right. You can't just ask a chatbot to write your field journal observation.
Right.
The human brain has to do the actual work.
Exactly. Because if the AI does the sense-making, the student's brain isn't building those redundant pathways we talked about. The technology is a tool, not a replacement for cognition.
Which brings us to the final piece of the sequence we mentioned earlier, save the evidence.
Right, the final step.
And I have a major question here about how you actually manage all of this.
How you grade it, you mean?
Yes. Because if these students are doing all this high-level field journaling, and they're investigating owl pellets, drawing ABC sketches, and revising their models, how on earth do you grade it? You can't just run a Scantron machine over a field journal.
No, you definitely can't. A traditional multiple-choice test cannot capture three-dimensional learning.
That's what they do.
Well, assessment in this system is an ongoing process. It includes daily formative evidence, performance tasks, and collecting larger portfolio artifacts. And the way they organize this is through digital portfolios and an ecosystem of micro-credentials, which are often referred to as digital badges.
Okay, I'm going to push back pretty hard on this.
Go for it.
I understand portfolios, but digital badges, come on. Aren't digital badges basically just the modern equivalent of a scratch and sniff gold star?
A lot of people think that, yeah.
Like, they sound like video game achievements. Does a 12-year-old actually care about a pixelated badge on a screen? How does that actually motivate a kid on a Friday afternoon?
It's a very fair skepticism, but a digital badge in the Bioforge system is not just a decorative sticker.
Okay.
These are verifiable credentials, and they are embedded with metadata.
Metadata.
Yeah. So if you click on a student's badge, it details exactly who issued it, the specific criteria required to earn it, and most importantly, it links directly to the actual evidence the student submitted to get it.
Oh, wow.
The curriculum uses a really great phrase to distinguish the two. They say, the portfolio holds the receipts. The badge recognizes what the receipts demonstrate.
The portfolio holds the receipts. The badge recognizes what the receipts demonstrate.
Exactly.
Okay, that makes it sound a lot more substantive than a gold star. But I still don't totally get the psychological motivation for the student. Why do they care?
Think about all the invisible skills that get lost in a traditional classroom.
Like what?
Like if a student gets a B in science, what does that actually mean? Did they test really well, but they were a terrible lab partner?
Right. Or did they struggle with the test, but they were a great leader?
Exactly. In Bioforge, the badges gamify the learning, yes, but they also make those durable skills visible. Students can earn credentials for leadership, or peer collaboration, or digital citizenship.
I see.
It allows them to build a highly personalized constellation of skills based on their own strengths. It gives them real agency. They aren't just trying to survive a test. They are actively building a professional profile.
All right, I can definitely see how that creates a totally different motivation structure for the kids.
It changes everything.
But I have to ask about the parents.
Yeah.
Because there is still formal reporting, right?
Of course, yeah.
The SIPS rubrics break things down into performance levels 1 through 4. But look, if I brought home a report card to my parents that said cross-cutting concepts, level 3, my mom wouldn't have had a clue what that meant.
Most parents wouldn't.
So how does this system actually communicate with the families sitting around the kitchen table?
And this is where the individual student report, or the ISR, comes in. They have completely redesigned how progress is communicated.
Okay, how so?
Well, instead of vague letter grades, students receive an instructional need level for different scientific practices.
What does that look like?
They are coded green, yellow, or red.
Oh, simple.
Right. Green means minimal additional instruction is needed. They are ready to extend the skill. Yellow means they need targeted practice. And red means they need significant reteaching.
Okay, that is definitely clearer than a random B minus. But what do the parents actually do with that information? Like, great, my kid is yellow, now what?
Well, the most innovative part of the ISR is that it actually includes QR codes tied directly to whatever specific skill the student is working on.
Oh, it's smart.
It doesn't just say, your child is struggling with Earth history and then just leave the parents feeling helpless. It gives them the exact tools to intervene.
Yes. Okay, the sources gave an incredible example of this.
The shark tooth one.
Yes. So let's say a student gets a yellow on supporting explanations about organisms that lived long ago. The parent scans the QR code on the report, and it takes them to a family resource page. And it gives the parents an actual script to use.
It tells them exactly what to say.
It says something like, imagine you are walking in the Midwestern U.S., far away from any ocean, and you find a rock with a shark tooth embedded inside.
Right.
And then it prompts the family to ask the student, how could a shark have been where there is no ocean today?
It's brilliant because it brings that anchor phenomenon directly into the home.
And it goes even further than that. It provides an activity where parents and students can physically print out and cut apart a diagram of rock layers and then order them chronologically right at the kitchen table.
It's so interactive.
It takes homework, which is usually this solitary struggle that ends in tears, and turns it into a collaborative, hands-on family discussion. It completely demystifies what is happening in the classroom for the parents.
It really does. And if we step back and kind of pull all of these threads together, the SIPS standards, that Monday through Thursday classroom rhythm, the field journals, ABC rubric, the portfolios holding the receipts, what we are looking at is a truly coherent, unified learning system.
It's not just a random collection of activities and badges.
No, not at all. The core philosophy of Bioforge is stated very clearly in the texts. Students should do the thinking that the learning is meant to develop.
Students should do the thinking that the learning is meant to develop. I love that. They aren't just memorizing what a scientist discovered 100 years ago. They are actually practicing the habits of mind that led to that discovery in the first place.
Exactly. And those habits of mind, particularly the Grinnell method of field journaling we discussed, are incredibly powerful far beyond the classroom.
Oh, for sure.
Because what that routine notice, learn, investigate, make sense really teaches a young person is how to separate raw, objective observation from their own subjective interpretation.
Which, let's be honest, is a skill society desperately needs right now. And that actually brings us to a final thought for you, the listener, to mull over as you go about your day. We started today by talking about the shift from a dusty, passive classroom to a living field station laboratory.
Right.
These seventh graders are being actively trained to meticulously document their observations, carefully separating objective data from their own assumptions.
It's a huge skill.
So here is the question for you. How might adopting that exact same field journal mindset, separating what you actually verifiably notice from what you assume or interpret, change the way you consume the daily flood of news and information in your own life?
That's a great question, because if a 12-year-old can learn to look at the world and demand verifiable evidence before jumping to a conclusion, well, perhaps we all can.